Hello, everybody. So what we're going to do today is we're going to, basically, we're just going to go through the review for exam 4. So what I'm going to do is open up the test review center and then just go through the topics one by one. And I'm just going to do the sample problems, just like you would if you were reviewing for the exam. Before we do that, though, I want to mention two things. So one thing is not related to exam 4 specifically. It's just related to all of the exams. And that is, if you missed one, let me know, and I will let you take that exam if you let me know in time, right? Because basically it has to be done probably by Friday because I don't know if you're going to have Canvas access after Friday. So if you missed an exam, let me know so you can make it up and not get a 0. Okay, just email me or send me a message in Canvas and we can take care of that. Okay, the second thing is that originally the topic list for exam 4 had a topic that was called, what was it called? The Net Change Theorem. And it wasn't a difficult topic or anything, but I decided that I'm going to take that problem off. So if you saw that topic, then it's gone now. Um, so no longer on there. And that's because specifically I did a lecture where I covered the net change theorem, but then the exact topic was not on the homework assignment. And so I feel like if the topic wasn't on the homework, then I shouldn't include it in the exam, even though we did a lecture on it. So I just took that off and I replaced it with a different question that was just kind of a topic that you would already be more familiar with. So anyway, with that being said, let's go ahead and get started. So I don't know what order the topics are presented in terms of does everybody get the same thing or not, but we'll do them in the order that I see them in. So the first one says, review evaluating definite integrals with the fundamental theorem of calculus. So the topic is definite integrals with the fundamental theorem. And so I think we have a couple of questions here. So let's start the review. Start review. Got it. So here's our first problem. So of course, I think you all get different ones, but mine is an integral from 1 to 16, negative 9x, it's wrong, to the negative 1/2 minus 3x to the positive 1/2 dx. Okay, and also while we're doing this, let me just turn this around for my calculator. Oh, come on, calculator, you must be here. How'd I lose it again? It's right here. Cool, I don't have to restart the video. All right, let's go ahead and get started. So what do you need to know for this topic? So before we do this question, what you need to know is this. So recall, definite integral from a to b of f of x dx is going to be capital F of x evaluated between a and b, which means you plug the b into the capital F, the a into the capital F, and subtract. So it looks like this, f of b minus f of a. And the relationship between the lowercase f and the uppercase f is that big F is an antiderivative of little f. Okay, and that's the fundamental theorem of calculus. That's what I just wrote there. One version of the fundamental theorem of calculus. So for this problem, what we need to do is step 1 is going to be find an antiderivative. So find the big F, basically, is what we need to do. And when we do, we're going to evaluate that between 1 and 16 because those are the limits that we have. So how do we do that? So in this case, what we're going to need is the power rule. So what's the power rule? The power rule is going to say we take the exponents, and what we're going to do is we are going to add 1 to this exponent. So this exponent is -1/2. So it's going to turn into, well, let's see, but the -9 just carried along, and then x to the +1/2, because we're going to add 1 to the -1/2. So -1/2 plus 1 is +1/2. And then you divide by that +1/2. And then we do the same thing for this one. So we have -3. So -3. The exponent here is +1/2. We're going to add 1. So that's going to go up to 3/2. And then you're going to divide that by 3/2, like that. And then before you proceed, you should simplify these fractions a little bit. So dividing by 1/2 is the same thing as multiplying by 2. So this is going to work out to -18 x to the 1/2. Dividing by 3/2 is the same thing as multiplying by 2/3. So it comes up like this. Like so. And then what we need to do now is we did this. Now we need to do this. So we plug the b and the a into the f of x. So plug the 16 in and plug the 1 in. So parentheses, -18, 16 to the 1/2, -2, 16 to the 3/2, parentheses. And then minus, do the same thing, but this time plug in the 1 here for x. -18, 1 to the 1/2, -2, 1 to the 3/2, like so. I recommend, especially if you're not comfortable with roots, that you grab a calculator that does these things symbolically. So in this case, I won't, I think, but I have a calculator here just in case. So -18 is -18, and then the square root of 16 is 4, -2, and then 16 to the 3/2. So the square root of 16 is 4, and then 4 to the 3rd power is 64. So like that. You can just type in on a calculator 16 exponent 3/2, and of course it'll tell you 64 as well. You don't have to do it by hand. And then here we got 18 times 1 to the 1/2, which is 1, and then minus 2 times 1 to the 3/2, which is also 1. So we have this. So then you work this out. So just grab a calculator. If you're being careful, maybe you want to work out each set of parentheses separately. So I've got -18 times 4, which is -72, minus 2 times 64. So I get -200 here, parentheses, minus. And then this is going to be -20. So -200 plus 20 is -180. And hopefully that's right. I'm going to type it in and we're going to see. Submit. Yay, got it right. So that is your definite integrals with the fundamental theorem. I'll do the next question if it looks different. Oh yeah, it is a little bit different. Oh, fancy. Okay, so we'll definitely do the next one because it's a little bit tricky. I guess I'll go to the next page. Why not? So the next question here is an integral from 1 to 4. -5x minus 9 over square root x to the -1 dx. Okay, so conceptually, this is no different than the previous problem. The difference is that with this denominator here, you're going to have to simplify before you try to integrate. So simplify before integrating. And let's go ahead and do that. So what you would do is you would take this integral from 1 to 4, and this is, -5x over square root x to the -1. minus 9 over square root x to the negative 1. It's kind of a dumb integral, to be honest. Then you have to remember that a square root is a 1/2 exponent. So this is a really negative 5x over x to the negative 1 to the 1/2. And then 9 over x to the negative 1, the 1/2. Like so. And then when you have an exponent to an exponent, you can multiply those exponents. So multiply the negative 1 times the 1/2. So you get x to the negative 1/2. X to the negative 1/2. We could have just done that once if we had done this, in step 1. So there we go. And then you also know that, well, there's two different ways to think about this. Either you can move this up to the numerator, or you can think about the properties of exponents for fractions. So I'll just write it for fractions here. So like if you have x to the a over x to the b, that's x to the a minus b, right? So if you apply that logic here, where this is an x to the 1, then what you're going to get is an integral 1 to 4 of, we have negative 5x, and then what's the exponent? Well, this is a positive 1, and then we're going to minus 1/2, right? So this is negative. So 1 minus 1/2, which is 3/2. And similarly here, you have 9x and a negative x to the negative 1/2 in the denominator is x to the positive 1/2 in the numerator, like so. And once you get to this point, now the problem is, the same difficulty level as the previous problem. So we're going to do our antiderivative stuff. So you add 1 to the power. 3/2 plus 1 is 5/2. Divide by 5/2. And then here, add 1 to 1/2. You get 3/2. Divide by 3/2. 1 to 4. Just like before, we want to simplify this. This is going to be negative 2x to the 5/2. Looks like, 9 over 3 is 3 times 2 is 6. So I think that's negative 6. X to the 3/2, 1 to 4. And then now we're going to plug in our 4 and our 1. So negative 2, 4 to the 5/2 minus 6, 4 to the 3/2 minus negative 2, 1 to the 5/2 minus 6, 1 to the 3/2. And there you go. Got to simplify these. So we got negative 2 times 4 to the 5/2. So that's 2 to the 5th, so that's 32. Again, you can punch that into a calculator if you are not good at doing those by hand. Same thing on the next one. 4 to the 1/2 is 2. 2 to the 3 is 8. Okay, and then here we got minus 2. The 1 to the exponent is 1, and then minus 6. 1 to the 3/2 is also 1. And then you work this out. So this is negative 64 minus 48 minus 8. So we worked this all out on a calculator. We got minus 64 minus 48 plus 8. Negative 104. Type it in just to check. Oops, where's the clicky click thing? Submit. Got it right. So we're done with that one. Awesome. So that's it for that topic. So next topic. Oops, that didn't bring me to the next topic. That brought me out of the stupid thing. Let me try again. Optional. All right. Yes. Okay. So new topic. So let me highlight this topic here real quick or something. Green or something. So there's the topic. So the next topic is make big. What is the next topic? derivative of an integral. So use fundamental theorem to compute the derivative of an integral. All right. And so here's what you need to know. It's very simple. This is very simple. People miss this at a high rate, but it's actually very simple here. So you recognize this by seeing a derivative of an integral. And then the integral is going to have like a constant down here, a variable up here. This variable and this variable match. And then here you have a function of a different variable like a t or something. So just any kind of function of t. And we derived this in class, but it turns out that all you have to do is you just put the x in for the t and you're done. So there's no work there, really. There are more complicated versions of this where there is some work to do, but there isn't on this one, I don't think. So here's what the problem says. It's very, very simple. As I said, you will see right now. So I guess we'll keep numbering. Call it number 3. So they say, find f prime given f is this integral, 0 to x, square root 5 plus cosine t. Now, sometimes they make that look very complicated, but that's not a big deal. So what do you have to do? Well, it's exactly what I showed here, right? You take the x, you put it in the function. So we should be taking this x and we should put it in this function for t. So this is a plus, not a t, but this is a t. All right, so what's the answer? Well, you're just basically going to rewrite this 5 plus cosine, but it's not cosine t, it's going to be cosine x. Okay, and you're done. That's the answer. Okay, so very, very simple. So simple that there's nothing to do, but people get it wrong all the time. So that is that. Next question. So how do I get the next question? I guess I have to click back. That's really frustrating. Okay. Back again, I guess. How do I, okay, click, start review. Oh, hate this. Why is this so bad? Back to the review list. Okay, I found the link. Okay, so yeah, then we got some substitution. Okay, next topic. So the next topic is substitution and trig functions. So integration with substitution, you need to know that going into Math 4B. We'll do one example here. Oh, this is a definite integral too. Oh, okay, well that's fine. We can do that. All right, so this integral is, oops. So this is, are we on problem 4, I guess? Integral pi over 6 down here, 11 pi over 6 up here, 32 cosine x sine squared x dx. Okay, and so what you have to think about here when you're trying integration by substitution is, first of all, you need to know that you need integration by substitution. So the way that you would know that is this is not a basic function, right? This is not a basic trig function because there's two trig functions multiplied together, and also there's an exponent. So it's not basic trig or power rule. And that's all you know how to do is trig functions and power rules. Uh, so we're stuck here. Well, we're not stuck, but we need integration by substitution. So try substitution. And before I do that, I want to rewrite this as 32. I'm going to put the cosine at the end. Write this sine x squared cosine x dx. Okay, so make sure you understand this, right? Like sine x quantity squared is what this means when you say sine squared x. That means the sine of x, and then you square it. Okay, so I haven't done anything, I just rewrote it. Okay, now when you're doing substitution, your general choice for doing a u substitution is that the inside function should probably be u. Usually, the inside function is u. Okay, usually. So in this problem, what that means is that the inside function is sine x, not the cosine, the sine x. So they kind of were trying to trick you by writing it this way. But if you pick cosine for u, you'll get it wrong. So you need to know that sine x should be your u. So we say, let u equal sine x. There's my substitution. We don't just need a u, we need a du. So to get a du, you're going to take the derivative of this function. Derivative of sine x is cosine x dx. If this du dx thing is confusing, you can think of it as coming from two steps. You can think of it as being u is sine x, so du dx, derivative of u with respect to x is cosine x. And then you can think about moving this dx over to the other side, like that. So that's where like the notation comes from, but usually we just write it the way I wrote it right here. From there, you're going to make replacements in your function. So you've got a couple things going on here. First of all, you have your sine x right here, right? Well, there's your sine x. And then also you have a cosine x dx, which is right here, cosine x dx. And if we made replacements for both of those, then we'll be getting rid of the sine x and the cosine x. So let's do that. So let's make the substitution. So our integral, I'm going to leave the limits off for the moment. 32 is 32. Sine x squared, sine x, but sine x is u. So that is u squared. And then you have cosine dx, cosine x dx. Cosine x dx is simply du. So there's my integral. So the integral turned into an easy integral. The only thing I have left to do is I have not dealt with these limits of integration yet. And we should deal with the limits of integration off to the side. So let us do that. So the way you deal with the limits of integration is we'll say, all right, translate. Well, I'll just say calculate new limits. New limits. So what you do for the limits is you just take one of the limits, like the old limit, the old bottom limit is pi over 6. So that's x equals pi over 6, right? But if x is pi over 6, what is u? Because we got u's here. So x is pi over 6. You use this calculation and you can calculate u. So we're going to basically plug x equals pi over 6 in here and say that u is, plug the pi over 6 in here for u, in for x, and we have sine pi over 6. So what is the sine of pi over 6? Either you know it or you check on a calculator. 1/2. Okay, so sine of pi over 6 is 1/2, and that was our bottom limit. So that's the bottom limit here. And then you do the same thing for the top limit. So the top limit was x equals 11 pi over 6, which means u is going to be sine of 11 pi over 6. So you calculate that. Believe that's going to be negative pi over 6, or sorry, negative 1/2, which again you can do on your calculator if you don't know it. Sine negative pi over 6, negative 1/2. And so that's your top limit. Now be careful here to get these in the right place, right? Like this was the bottom limit, so that's the bottom limit. This is the top limit, so this is the top limit. And over here, it looks weird to have the negative number up top, but that's just the way this one came up. It's perfectly valid. Okay? So once you make this substitution, then we can just finish the integral like normal, like the previous problems, to be honest. So let's just solve the integral. So the way you would solve this integral is you need an antiderivative. So again, we're going to add 1 to the power. I've done this a couple of times. Add 1 to the power, you get a 3. Divide by the new power, which is a 3. And then we plug in our limits. And these limits are for you, so you can plug them in for you. You don't have to go worry about the sign or anything anymore. So we have 32 negative 1/2 to the 3 over 3 minus 32 positive 1/2 to the 3 over 3. So you calculate these out. This works out to 32 negative 1/8 over 3 minus 32 positive 1/8 over 3. I think I said 2, didn't I? On the previous one, over 3. So you work these out. This is going to be 32 over 8 is 4. So this is negative 4/3 minus 4/3, which is minus 8/3. So that should be my answer, is minus 8 over 3. And that is correct. Okay, so that's substitution. We're going to do another substitution next, I believe. Figure out how to do it. Okay, the next problem is exactly the same. Back to review list. Substitution and the power rule. Okay. Were we numbering these? Yeah, we're on number 5. So what substitution and the power rule look like? Well, concept's the same. So Newton Alta's throwing some shade at me. It just popped up of its own accord. Keep trying. Everyone learns at their own pace. You got them all right, so leave me alone. Okay, so here we go. So this is going to be a substitution integral, similar to the previous one. Why is it substitution? It's substitution because you either have to do substitution or multiply it all out. So let me just say that. So you would, well, first of all, let me just say it's not basic because you have a function multiplied by another function. So a function 7x cubed multiplied by another function 6x plus 1, 6x to the 4th plus 1 to the 6th. So it's not just regular power rule. It's more complicated than that. Okay. So you have two choices. Number one is going to be simplify it, which involves multiplying this out, which is insane. Nobody's going to multiply out 6x to the fourth plus 1 to the sixth power unless they really, really have to. So multiply it all out, but 6x to the fourth plus 1 to the sixth is, ridiculous to multiply out. Or two, use substitution. So of course, that's what we're going to do is we're going to use substitution. So they're careful to give you an integral where you would never do this with that first method, okay? So if you want to, you have bad instincts, don't do that. Okay, so here we go. So this is our integral. So obviously we're going to use substitution. So this is what we're actually going to do. Okay, so again, just like the previous problem, you choose your u to be the inside function. So choose u to be the inside function. What's the inside function? This, right? Very similar to that sine and cosine problem, right? Where you can see that the sine is inside the square. Well, 6x plus 4 to the 1 is inside the sixth power. So that should be the obvious choice. Okay, if you get this wrong, it's not going to work out. So we try. U is going to be 6x to the fourth plus 1. Notice that we're just taking the inside function. We're not taking that exponent with it. So u is 6x to the fourth plus 1. Du, you're going to take the derivative of this. So what's the derivative of 6x to the fourth plus 1? Well, this is a derivative, so power rule. You bring the 4 down in front, so you get 24. X to the 3, we're subtracting 1 from the exponent, and then a dx. Okay? So, right, for substitution, you do a derivative in the middle of your integral. So it's easy to get mixed up between antiderivatives and derivatives, but this was a derivative here. Okay? So what I see here is, let me just get rid of that. This 6x to the fourth plus 1, we know that is u, right? So we know what this is. Okay? But if you compare the du thing here, what you'll see is that it doesn't match up perfectly, right? Like the dx is dx. The x to the 3 is x to the 3, but this is a 24 and this is a 7. So these don't match up exactly, right? So what you have to do is think about that and say, well, this matches, so this matches, right? So we actually just don't want that 24 here. So you move the 24 over to the other side. Du over 24 equals x to the 3 dx. And now it's better to have it this way. Okay, so let me just rewrite this integral here. So we have the integral, what was it? I'm going to write -7 parentheses 6x to the fourth plus 1 to the sixth. And what I'm going to do is I'm going to move this x to the 3 over next to the dx. That's why I didn't write it at the beginning. So this is the integral, right? And now we can see that the x cubed dx is going to match up with the x cubed dx. And then we also have this part right here, the 6x to the 1 matches up with the 6x to the 4 plus 1. So let's make our substitution then. So we have integral -7. This is u. So u to the 6th. This is du, right? Almost du. It is du over 24. Okay, so my integral is, if I'm going to collect the 7 and the 24 just off to the side and have negative 7 over 24 integral u to the 6th du. Okay, so from there, now we can find our antiderivative, right? We're just going to do this integral now. So negative 7 over 24. And then how do you integrate u to the 6th? Well, you add 1 to the power, and then you divide by the power, and then you add c. So this is, right now, what we've got is, I think we can actually also cancel these 7s. So what we got is, it looks like negative 1 over 24 u to the 7th plus c when we cancel those 7s. And we're almost done now, but we have one step here that we have to do that we did not have to do on the previous problem, and that is put in what u is, right? Because we have this u right here, but our original problem didn't have u's, it had x's. So go back to x's. Don't answer u. Okay, so you just go back up here and say, well, what is u? U is 6x to the 4th plus 1. So you just make that replacement right here and say that that is going to be negative 1 over 24, 6x to the 4th plus 1 to the 7th plus c. And that's your answer, although they ask you not to type in the plus c. And that's substitution. So we did one substitution that was indefinite integral. Your answer is a function. And then we did one substitution that was a definite integral where your answer is a number, and they had slight differences, right? Here you had to translate the limits. Here you have to substitute back to the original variable. So slightly different things at the end of the problem. But that is that. All right, back to the review list. What is next? Area bounded by two curves. Okay. Why will you not? Oh, there it is. I feel like a dummy. I'm like, I don't know how to use Newton Alta. So I keep clicking on the wrong thing. Um, area between curves. What number are we on? 6? Okay, so it says determine the area in square units, which I'm not going to write. Determine the area between f of x equals negative 4x squared plus x minus 25. They actually say that this one's above, and no, not above that. I wrote that wrong. Bounded above by this, and then bounded below by g of x equals whatever it is, negative 3x squared plus 17x plus 38. Okay, so just in general, before we do this problem, which actually makes me want to move this down a little bit. So the deal is that you've got this situation going on. We've got a graph. You have a top curve, which they tell us, in this case, it's f of x. So may as well use that. You have a bottom curve, which is g of x. These intersect at two places, here and here, right? Right there, and then right here. And that's also why I referred to this as being the top curve, even though down here it's below, because in this region, the pink curve is on top and the purple is on the bottom. Okay, and then if you have this kind of setup, and we want this area between them, then the area is simply going to be integral from a to b, and then you need your top curve minus your bottom curve, dx. Okay, so you have to, we already know a lot. We know the f and the g because they're given to us. So that part's easy. So what we need is we actually have to figure out where these two things intersect. You can use a computer, or you can do it by hand. So basically I can look at these and see like negative 4x squared and negative 3x squared. These are both parabolas and they're both upside down. So I know that basically, I don't know where the axis is, but they're upside down parabolas. So I know I've got one like that. I guess it would be f of x. And then you must have one this, and this one would be g of x. Right? So f of x is on top, and then g of x is on bottom, and we don't know where they intersect right now. We don't know the a and the b. So that's what we have to figure out, either on a computer or by hand. So if you wanted to find them by hand, what you would do is you would set f and g equal to each other. And so that's what we'll do. So we'll find a and b by setting f of x equals g of x and solving for x. So what will we get? We got negative 4x squared plus x minus 25. That's f equals negative 3x squared plus 17x plus 38. All right. So move everything to one side. So just move everything over there. So we get 0 equals, and I'm just going to work it out just kind of in my head here. Negative 3x squared, and we're moving this over, so this will be plus 4x squared. So that'll be x squared. We have 17x. When we move this over, the x will go over as a negative x. So that'll be a net plus 16x. And then we got 38. We're moving the 25 over. It'll move over as a positive 25. So 38 plus 25, which is 63. So plus 63. Okay, and we're trying to solve this for x. So we'll try to factor this. So we're looking for numbers that multiply to 63 and add up to 16. So, I mean, obviously that's 9 and 7, right? Multiply to 63 and add up to 16. So this is going to be 0 equals x plus 9, x plus 7, like that, which tells you x equals negative 9, x equals negative 7 are your solutions. All right, so that's where your a and your b are going to come from. So those are the a and the b. So my integral then is going to be the integral of f of x minus g of x. We have to plug those in, but my limits are going to be negative 9 up to negative 7. Okay, and you could have used a computer. If you typed this into the computer, it should have just popped out the 9 and 7. Or if you just graphed both of these on like Desmos, you would have been able just to click on where it looked like they were intersecting and figured out that they were at negative 9 and negative 7. So lots of ways to come up with those. Okay, So let's do this. So we have integral from -9 to -7, f of x, which is -4x1, right? -4x squared plus x minus 25 minus -3x squared plus 17x plus 38 dx. Now this looks like a calculation we already did, but we just have to be careful to get the sign right. So -4x squared minus minus is a plus 3x squared, so that's going to be -x squared. X minus 17x, so that's going to be -16x. -25 minus 38, it's going to be -63. So those are the same numbers we already saw, they just happen to be in the opposite sign, and that's fine. This is just the way it works out. So from here, you just solve the integral the way we've solved many integrals today already. So add 1 to the exponent, divide by the new exponent. Same thing here. Add 1 to the exponent to get a 2, divide by 2. And here, just 63x from -9 to -7. So you put in the -7 first. -7 cubed over 3 minus 16 -7 squared over 2 minus 63 times 7, -7, minus all the same stuff, but with 9s, minus 9 cubed over 3 minus 16 minus 9 squared over 2 minus 63 times -9. And we have to work this all out. It's a little bit tedious. I guess all of them are, but let's see here. So 7 to the third power, what's that? 343. So this is, that'll be -343, and then the negative, which is going to be positive. I'm just waiting for a notification to move out of my way before I can write again. So I think this works out to 343 over 3 minus 7 squared is 49. 49 times 16 is 784 over 2. And then here we got minus 63 times minus 7, which is positive 441. Minus over here, add 9 to 3 over 3. I'm just going to do that while we're at it. So again, that's going to be positive on top. So this works out to a positive 243 here. 9 squared, of course, is 81. 81 times 16 is 1296 over 2 is 648. Should that be positive or negative? Looks like negative. And then 63 times 9, 567. That's a plus. Okay, so we got to work these all out. 343 over 3 minus 784 over 2 plus 441. So this is 490 over 3 minus 243 minus 648 plus 567, 162. So 490 over 3 minus 162, 4/3. Doesn't look like it was going to come up that simple, huh? 4/3. So like there's just really not that much area between them, right? Because the two curves are very close together. All right, 4/3. I'll type that in just to double check that it's correct. 4 over 3. Submit, but it will be because I'm smart. Okay, disk method. The end is within sight. With Alta, everyone has a chance to master the material. Keep at it, bug. All right, disk method. So remember what this is about. We did this pretty recently. So the deal is you've got a function. You're going to have a little section of the function here that gets rotated around an axis, and it turns it into a three-dimensional shape. That's the worst thing I can draw. I'm drawing at a really awkward angle here, by the way, just so you know. Okay. So you rotate that around and it turns into what we call a solid of revolution, and this is a solid with some volume. What's the volume? Well, the volume is given by the integral from a to b of pi the radius squared dx. Now, what's the radius, you ask? The radius is measured from the axis of rotation up to the curve. So this distance is the radius. That's needed better color. So that's the radius right here, from here to here. But that just happens to be the function height. So really the f of x is the r of x in most of these problems. Okay, but that's how you calculate it. And we should have an easy problem for this. No, in quotes, easy. All right, what is our question? So our question is, what number is our question? 7, yes, 7. So they say R is bounded by f of x equals 6 square root 7 cosine x. They like square roots here, by the way, because they know you're going to square this anyway, and that's going to make the square root go away. X equals negative pi over 2, x equals negative pi over 6, and the x-axis. So disk method, and we're rotating around the x-axis, which is what I drew in the picture as well. All right, so here's what's going on. And to draw the picture, please just make a straight line. Okay. So basically, this is a curve. I'm not going to draw like exactly what it is. It only exists when the cosine is positive. So like from negative pi over 2 to positive pi over 2, for example, is where this thing can exist. So wait, is that right? Yeah, that's right. So what you've got basically is negative pi over 2 here, positive pi over 2 here. And, you know, it doesn't look quite like the cosine because it's got a square root on it, but something like this. And then, so that's your top curve. And then on the left, you're bounded by negative pi over 2, which is right here. On the right, you're bounded by negative pi over 6, which we didn't draw, but it's, you know, somewhere in here. Like that, which means you've got a little section of the graph that looks like this. That's the region we're talking about. Okay, and then that's going to get rotated around the x-axis. And so it's going to turn into basically a little shallow bowl when you rotate it around. So that's the deal. And then what's the volume going to be? Well, we know exactly how to calculate that. The disk method tells us. So we're going to have the volume is going to be the integral from a to b. We're going from here to here, so a to b. So negative pi over 2 to negative pi over 6. Pi, we know we've got our radius, which I haven't done yet. What's the radius? Well, you measure from the axis, which is here, curve is here. So that's just going to be, the height happens to be the function. So the radius of x, with the radius as a function of x is just going to be actually f of x, which is given to us as 6 square root 7 cosine x. So what we get is this is integral negative pi over 2, negative pi over 6, pi 6 square root 7 cosine x squared dx. Right? Wait, one of those should have been 7. Okay, so let me just rewrite this one more time. So what are we doing here? Well, first of all, you can take that pi out. You can always take the pi out of the integral if you want. And then we need to square this. And be careful when you square this, right? Both of these things are squared, the 6 and the square root. So when you square the 6, you get 36. And when you square the square root's going to go away. So you have a 7 cosine x. Not 7 squared, because the 7 was in the square root. So when you square it, it doesn't become 49. The square root just goes away. So we're here. I can multiply the 36 times the 7, 252. I'm going to write it down here. So we have 252 pi integral. I just kept taking the constants out. And then we just have a cosine x dx here. All right, so that's the integral set up. Once the integral is set up, all you need to do is just solve the integral the way we've solved a bunch of integrals. And this is not a hard integral either. You need an antiderivative. Antiderivative of positive cosine is positive sine. Oops, it's a 2. And then you plug in your endpoint. So 252 pi, plug the pi over 6 in here, sine negative pi over 6, minus 252 pi, parentheses, sine, plug the bottom limit in, negative pi over 2, like this. So you work this out. So this is going to be sine negative pi over 6 is negative 1/2. Minus 252 pi sine of pi over 2, negative pi over 2. Sine of negative pi over 2 is negative 1. So what do we get? Well, we can work this out. So work this out, 252 over 2, 126. So this is negative 126 pi. And then negative makes it positive, so plus 252 pi. And then we add those together, and I think we get positive 126. And that's the area, or volume, sorry, of this three-dimensional shape right here. 126 pi. And that is correct. Okay, 2 problems left. Oh man, we're over, well no, we're at an hour. All right, let's hurry up, finish this up. Arc length. All right, so arc length, basic idea. Now, whether you're doing the integral in terms of x or whether you're doing the integral in terms of y affects things. But for us, basically, if this curve is y equals f of x, then the length of the curve is an integral from a to b, square root 1 plus f prime of x. I mostly called that dy dx when I did the lecture. Yeah, so there it is. And I guess I'll draw it the other way too. You can have your curve like this, and you can have bounds on your y-axis, a and b there. I guess maybe I'll call them c and d or something. C, D. And in order to do it this way, your curve would need to be x is a function of y, right? So the variables are kind of reversed, and your limits of integration are here. But if you have that, then your length would be the integral from c to d of 1 plus g prime of y squared dy. So I'm just writing that because technically you could use either of these for some problems, and some you need to use one or the other. But it should be the first one for you guys, I assume. So yeah. So let's look at this. What number are we on? 8. I'm just going to say we're on 8. So let C for curve, be f of x equals 6x to the 6 plus 1 over the interval 6 less than x less than 8. Set up the integral for the length of the curve. All right, so this is pretty simple conceptually. So 6 and 8 are on the x-axis, right? Your curve is somewhere in there, like that. So we want just a section of the curve here. This is what they're calling C. And we want the integral for the length of that. So all you got to do is take this function here, and we're going to put in our information. That's all. So what's our f of x? Basically is what we need. So f of x was 6x to the 6th plus 1. So we need the derivative of that, f prime. So again, you bring the power down in front, 36, x to the 5th. Okay. And then we set up our integral. So the length is the integral. Hopefully it's clear that your bounds should be 6 and 8. You have your square root, 1 plus f prime, that's this one, squared. That's your integral. And then all you got to do, I think all they expect you to do here is actually square this here. So square the 36. 36 squared is 1296. And then for the exponent, x to the 5th squared, you multiply those. So x to the 10th. And this is the answer that they expected because you can't solve that integral. It's impossible for us. Okay, so that's why they just ask you for the integral. They don't ask you to actually solve the whole thing. So let me just click it, hit submit, continue, and then, oh, do we actually have to do one of these? I guess we better do one of these. kind of losing steam here though. So let's, two problems left. All right, so f of x is 1/6 x to the 3 plus 1 over 2x, oh no, for 1 less than x less than 4, right? And then what we want is find the length of the curve. So it's the same problem as the previous one, but different curve. Okay, so again, same setup. 1 is somewhere, 4 is somewhere. Your curve is there. We want the section there, and then the length is integral from a to b square root 1 plus f prime of x quantity squared dx. Okay, so the derivative's a little bit harder here, and they actually expect us to solve this one, so we have to be careful. So let's write f of x 1/6 x to the 3, and I'm going to be careful here with this. 1 over 2x can be written as 1/2 x to the negative 1. Haven't done the derivative yet, that's just what 1 over 2x is. Okay, now let's take the derivative. So f prime is, you take the 3 down in front, 1/2 x squared. Here you take the negative 1 down in front, makes it negative 1/2 x. Negative 1 minus 1 is negative 2. So there's my derivative, which I can write this way, 1/2 x squared minus 1 over 2x squared. That's my derivative, okay? So now let's set up the length. Integral from a to b, square root, 1 plus f prime of x squared dx, and we put in all the stuff we know. So what do we know? We know the limits of integration are 1 and 4 from our picture, from the given information. We have our derivative here to plug in for the f prime. 1 plus parentheses 1/2 x squared minus 1 over 2x squared dx. Okay, now they expect us to solve this. So we actually have to simplify and integrate this. And I did this in the lecture, so I'm going to do it in less detail here, but we're going to do it. So you've got to basically multiply this out. Right, because you got the square there. So let's do that. You're going to end up with 1/4 x to the 4th. The middle term is going to be when you multiply these. So, okay. So when you multiply these, you're going to get 1/2 times 1/2 is 1/4. And then the x squareds are going to cancel. So you're going to end up with negative 1/4 and then negative 1/4. So it's going to be negative 1/2 for the middle term. And then when you multiply this by itself, you're going to end up with plus 1 over 4x to the 4th dx. Okay, so you multiply that out, you get this. Now at this point, you want to combine this 1 and this negative 1/2. It's going to turn into a positive 1/2. Right, minus 1/2 plus 1. Like so. Okay, now what you want to recognize about this is that this thing that you multiplied out came out like this, right? And this had a minus 1/2 here. And the only difference between this line and this whole thing is that this is a minus 1/2 here and this is a plus 1/2 here. And that's a clue that this is going to end up being something squared, just like this was. this is what we call a perfect square trinomial, which again, I covered a lot in one of the lectures on the lecture on arc length, and then arc length sample problems, I think. So this is a perfect square. It's the form a squared plus 2ab plus b squared, okay, which factors into a plus b squared. And so what the reason that helps us is because all we need to do is know what this is squared, or sorry, what this is the square of, and what this is the square of, and that's the a and the b. So I'm just gonna put it here. And again, to help you think of that, remember that this right here looks a lot like this. Just this is a plus, this is a minus, and this right here is this thing squared. So really what we're going to end up with down below is this exact thing, but with a plus here instead of a minus. Because this minus gave you this minus, but now it's a plus. So when we factor this, it's going to be a plus. So it's going to look like this. So it's going to be parentheses 1/2 x squared plus 1 over 2x squared squared. And you can go through the lecture if that's complicated for you. Okay, so at this point, we get to where we want to cancel this square root with a square. And we end up with 1, 4, cancel the square root with the square, so we're left with just parentheses 1/2 x squared plus 1 over 2x squared, but I'm going to write it this way, 1 over 2x to the negative 2. All right? And then now we can solve this. So the way we've solved lots of integrals. So add 1 to the power, makes a 3, divide by 3. Add 1 to the power here, turns into a negative 1, divide by negative 1. From 1 to 4. Before I do that, this is x to the 3 over 6 plus, actually minus, looks like 1 over 2x, I think. So from 1 to 4. Plug in the 4, plug in the 1. Many times we have done this. 4 to the 3 over 6 minus 1 over 2 times 4. Then plug in the 1. 1 cubed over 6 minus 1/2. So what do we get? We get 64 over 6 minus 1 over 8. I'm just going to deal with the parentheses now. Minus 1/6 plus 1/2 minus minus. So we punch all this into a calculator. 64 over 6 minus 1 over 8 minus 1 over 6 plus 1 over 2, 87 over 8. Is this right? I hope so. 87 over 8. Submit. Yay. So, I mean, that's going to be the trickiest one to do. And the trouble is simplifying the stuff in the square root. So that's a tough question. Okay, that's it for arc length. Now, the last thing is actually the most recent lecture, implicit differentiation, okay? So let me write the topic. Okay. So remember the way this works is if you take the derivative with respect to x of a function of x, you do it like normal. Okay, and as an example, right, d dx of, let's say, x cubed is 3x squared, right? So that's easy. But if you do d dx of, let's say, g of y, so a function of y now, then um, what you get is d prime of y dy dx. And so the difference is you've got to tack on this extra dy dx, and that's what the chain rule says you have to do. And it's because this is a function with respect to x, and sorry, the derivative with respect to x of a function of y. And you're assuming that y is a function of x. And that means the chain rule tacks this on. Okay, that's not a derivation, I'm just stating it. From a practical standpoint, what that means is if you do the derivative with respect to x of y cubed instead of x cubed, you do the derivative just like you did right here. So 3x squared, in this case 3y squared, but you have to tack on this dy dx. Okay? So if you remember that rule, then you're going to take the derivative and then you have to solve for dy dx with algebra. Okay? So let's just do the problem. I think we're on problem 9. So the problem says find dy dx if x minus 2x to the 5th y to the 4th equals 1. Okay? And you have to type in what dy dx is. So let's start here. So x minus 2x to the 5th y to the 4th equals 1. So the way you solve this, so this is the start, then you're going to basically apply your derivative. So apply d dx to both sides. So you end up with d dx, d dx, like this. Okay, and now you take the derivative of both sides with respect to x, keeping in mind that you have to treat the functions with the y's in it differently. Okay, so move, not you, I'm talking to notifications again. So the derivative, the derivative of 1, of course, is 0. That's easy. Now over here, this derivative, well, we got two pieces. So first we take the derivative with respect to x of x, which is simply 1. And then minus, now we have the derivative with respect to x of 2x to the 5th y to the 4th. Now, I'm just going to write this out so I can look at it. You don't have to do this. You can just do it in one line. But the point that I'm going to say here, the reason I did this is this and this are two functions multiplied together, right? So when we take this derivative, we're going to have to use the product rule. And that's what makes this a little bit tricky. So we do the product rule. Remember the product rule, like if I do fg prime, it's f prime g plus f g prime. So let's apply that rule here. We're going to get 1 minus, and then, so this is my f, 2x to the 5th. This is my g. So f prime g plus f g prime. So there's my product rule. And of course that equals 0 still. Now the two things with primes on it still need derivatives. So let's take the derivatives of the things with the primes. So here, this is the derivative with respect to x of an x function. So we just apply the normal power rule, bring the 5 down in front. 10x, subtract 1 from the power. 10x to the 4th. And then the y to the 4th has no prime, so we just write it. Now here we have 2x to the 5th, no prime, so 2x to the 5th. And now we have y to the 4th prime. So this is a derivative, the derivative of y to the 4th. the derivative of y to the fourth is 4y to the 3. That's the power rule, but we just took the derivative of a y function, and we know that means you just throw a dy dx on the end. That. So now you have to solve for dy dx with algebra. So it's not going to be that hard. You're just going to take this stuff, move it over to the right. So you're going to end up with 2x to the fifth. Actually, let's just multiply a little bit here. So 2 times 4 is 8, right? So this term right here turns into 2. Nope, I just said it turns into an 8. 2 times 4 is 8x to the fifth, y to the 3, dy dx equals, and the stuff that I underlined in pink is going over to the right, which means we're subtracting it to the right, so the signs are going to change. So it's going to be -1 plus 10x to the fourth, y to the fourth. Okay, and we're trying to get dy dx by itself, so we're going to divide the 8x to the fifth y cubed off to the other side, and we end up with dy dx equals, I should rewrite this in the opposite order just to make the signs look nicer, 10x to the fourth, y to the fourth minus 1 over, and we're dividing this off to the other side, so we get 8x to the fifth, y to the 3. And that's my answer. So the algebra is typically what's hard on these, especially if you have dy dx in multiple places. Again, I recommend that you check out the lecture for this topic. There's a lecture that has extra practice problems. So see lectures on what was this called? Implicit differentiation. Or more sample problems of that. Okay, so I think that's it. Let me look at this. Back to review list. Yeah, we did everything. So if you can do everything on this list, then you are in good shape for your exam. And if you can't, well, you're in less good shape for your exam. Again, keep in mind, if you missed an exam, let me know. And Net Change Theorem's not on there, and I will talk to you guys later.